Hello everyone, welcome to 2.3, the limit laws. Here we have these objectives where we learn about the basic limit laws. Then we will evaluate the limit of a function, and then we'll also consider functions that are polynomial and rational, and then wind up with squeeze theorem. You can see here limit laws are presented. Let's look at the definition or the premise of these laws, where we take two functions, f and g, okay, and then we define it over some open interval. Now we assume that there are limits L and M that exist such that limit f of x as x approaches a is L, and limit g of x as x approaches a is M. And we're going to need C somewhere in one of the laws, so we call C as a constant. So what we're saying is, in the sum law, you take the sum of the functions, right? You add the functions. You know that is possible because of combination of functions. If you add f and g, the two functions, and then take its limit, the law says, well, it is the same as if you took the limits individually and then summed them. Yeah. So limit of f of x plus g of x together is the same as limit of f of x plus limit of g of x, where each one goes to a certain limit, like limit f of x is capital L and limit g of x is capital M. Then we go for the difference law. That is also similar. So if you take the limit of the difference, yeah, of f and g, then it gives you the difference of the individual limits. So limit of f of x minus limit of g of x. So limit of the difference is the difference of the limits. Previously, limit of the sum is the sum of the limits. Constant multiple law says, well, if your function is multiplied by a constant, right, then the limit is does not affect that constant, meaning the constant can be pulled out and the limit for the function alone can be applied. That makes sense because the whole idea of limit is trying to see what happens as x approaches a. And if c is a constant, then it doesn't matter what x approaches, doesn't matter what it approaches, you will always have the c, available. So c times L is the result of that. Then we have the product law. So if f and g are two functions that are being multiplied and you take their limit, then it's the same as taking their individual limits and then multiplying them. So limit of the product is the product of the limits, L times M. Likewise, limit of the quotient is the quotient of their limits, L over M, of course with the condition that M is not equal to 0. And power law says if you had a power for your function, this is really interesting because it will come in handy. If you have the power n for your function, then we're saying, hey, we can bring the limit inside and find the limit of the function first and then raise it to the power n. That is very powerful because what you can do is find the limit of f of x, which is L, or number, that power n. So L power n is a numerical quantity that can be easily determined. Similarly, the root law says if you had a radical, a root for your function, and for which you're trying to find the limit, the law allows you to find the limit of the function, and to that answer, you can take the radical. So we say limit of the radical is the radical of the limit. Yeah? So it is radical n, nth root of L. Okay, and so we're going to need combination of these laws or rules as we move through the problems. So let's take a look at the first one. Let's insert some space here. Use the limit laws to evaluate limit 4x plus 2. So let's go ahead and do this. So let me write that here. Limit 4x plus 2 as x approaches -3. The sum law allows us to apply the limit for each of the sum, the addendum. So that, and you have x approaches -3. And I will say here it's because of the sum law. Okay. And then if you look at this, within the sum law, I mean, we've applied it. Now let's take a look at the first term. You have 4x in your function position, right? But then it's x that's multiplied by 4. 4 is a constant. So by constant multiple law, you can pull the 4 out and then say it's 4 limit x as x approaches -3 plus, this is limit of a constant, okay? Let me write it anyway. And then I say constant multiple law. Okay. And then one more step. Now you have 4 times -3, because limit of x as x approaches -3, you can plug in the -3 in the place of x. We saw this in the previous lecture. And here again, limit of a constant is the constant itself, because there is no x to plug in for. So you get back the constant. So this in turn gives you -12 plus 2, which is -10. So the answer is -10 for limit f 4x plus 2 as x approaches -3. Okay. And this example here kind of teaches us that we could be using the laws, repeatedly as much as you need, or as in whatever combination you need, so as to find the limit. Okay. So here we go. Now you can see this is already a quotient setup. So in your mind, you can already think of using the quotient rule. 2x squared minus 3x plus 1. So I'm going to separate this as limit x approaches 2 here, and then 2x squared minus 3x plus 1 over and we're able to do this because of the quotient rule. You always want to provide the rule that supports this move, because we want to keep it mathematically valid in every step. Okay. And then on the top, you can separate these terms again by sum and difference law. And I'll do the same thing for the denominator. Yeah. All right. If I do it elaborately, you can see that it takes many steps. But being the first time you're looking at this, it's okay to give it the time and the number of steps it needs to begin to see how it works. Okay. So then we have the 2 that can be pulled out. And the 3 can be pulled out here. And this is a constant. We'll keep that in mind. Okay. All right, so when you have just the limit x, like in this case, right, in the middle term here, limit x is the simplified form wherein you can plug in for x as 2. But if you look at this x here, this has a square, x squared, and this x down here has an x cubed. So the simplest form should be either just an x or a constant, but we have the square and the cube, for which we go back to the power formula. So let me quickly take you here. See the power law? The power law says, well, if I have a power, I can first find the limit, and then to that answer, I can apply the power. So we're going to do that here. I need more space. Okay. 2 limit x x approaches 2. I'm going to square that. And then here too, the cubed. So I'm going to take the limit first, and then to that answer, we will cube that answer. All right, so one more step, and then we will be able to display our answer. Now we can plug in for 2. That's a constant, so that is 1. I hope you can follow with me. I'm plugging in because I brought them all to their simplest form. I could just plug in for what value the x approaches. And so that's going to be, I'm sorry, 2. 2 should be cubed. Plus 4. Okay. All right, so that's going to be 8 minus 6 plus 1. Okay, 1 over 8 plus. Okay, so that reduces to this. Yeah, and let me box it. Okay, I hope you can see that this is a reduced answer because you actually have 3 over 12, which reduces to 1 over 4. So we found the limit to the given quotient. Over time, you don't have to do it so elaborately. You'll begin to see that, you know, these things are going to happen, and then you will begin to reduce or eliminate a few additional steps. Next, we go to the idea of how to handle limits for polynomial functions and rational functions. What's really neat is for polynomial functions, you just plug in for wherever you see x in your polynomial, you're going to plug in for x as a because x approaches a. And that is basically a combination of sum and difference rules. And, you know, we're kind of looking at the polynomial collectively, and then you can use the rule right away. So you don't have to separate them individually. For instance, in the previous example, if you let me take you right back here to the top one. If you look at this numerator is a polynomial, right? 2x squared minus 3x plus 1, it's a polynomial of degree 2. And the denominator separately can be seen as a polynomial of degree 3. So what it says is you don't have to do this sum and difference rule individually, because you can see it as a polynomial. If you can establish it's a polynomial, you can go ahead and plug in this 2 directly for your x's, and likewise for the denominator. And then what it says in terms of, go down here, rational also it says, well, the rational is nothing but a ratio of 2 polynomial functions. So you have a polynomial over a polynomial, so we can go ahead and plug in for all your x's by a, the given value that x approaches. So if you go back to the same problem we just saw, this problem actually is a polynomial over a polynomial, so it is a rational function, which means we could directly apply the to substitute for x as 2 in your polynomial, in your rational function. So that's what this is. So we'll take a look at this example. It's a similar one, but you can clearly see that this is a rational function. So previously, we would have separated them by quotient rule. Everything holds true, just that we're now going to see it in terms of a rational function. So you can see that your calculation actually gets pretty quick. So limit 2x squared minus 3x plus 1 over 5x plus 4. All I do is simply remember to draw the shells because you're going to substitute. And wherever x occurs, I'm plugging in 3 because x approaches 3, right? Do the calculations, it comes out as 10 over 19. And that was really quick, isn't it? We could have done this in the previous technique, and it would have taken extra steps. But because of this rule that allows us to find the limit of a rational function by simply evaluating the value, it makes this technique really, really saves a lot of time and steps. Okay. What about evaluating a limit by factoring and canceling? Okay, let's see what that is. Now, when you have rational functions, if you can find a way to reduce your function, then you can definitely try and use that. Now, you always want to see where your function becomes undefined and things like that. You always want to take care of that. Okay. So this comes in handy, especially when you have a situation where you get an indeterminate form, a form where you have like 0 over 0 and things like that, where your function becomes undefined. So for instance, in this case, say your x is 3. Then your function, right, x squared minus 3x over 2x squared minus 5x minus 3. Try plugging in 3. You can pause at this time and quickly see if you can plug in. And then you'll see that 3 squared minus 3 times 3 over 2 times 3 squared minus 5 times 3 minus 3. On the top you get a 0, right? Over 0. 18 minus 15 minus 3. So you get 0 over 0. For these situations, you want to really factor and cancel so that you can remove the condition where it becomes 0 over 0. So factoring and canceling is a good strategy. So let's write this. I'll write the limit because we're just kind of at this point dragging it along. We're not applying the limit yet because we're trying to do algebra here. So x can be pulled out. So you get x minus 3 over, do the techniques that you know, the X method, the AC method. In this case, you have to use the AC method. Things that we have taught previously in an algebra course, intermediate algebra, use those techniques. We've also learned about quadratic formulas. So you have to use that and bring it back in the factored form. So recall these concepts, okay, where you try to find the factors. And so you get factors for this as x minus 3 times 2x plus 1, okay? So you got that. By the side, let me just quickly recall, oops. So say you have this 2x squared minus 5x minus 3. The AC method, at least what, it's one of the methods, is that you look at A times C, which is 2 times negative 3, so that's negative 6, and B is negative 5. So you look for two numbers whose product is negative 6 and whose sum is negative 5. So you list out all the factors that will work, and then you have to, according to this AC method, you have 2x squared, and then those two numbers, you'd have to figure out what those numbers could be. So it could be negative 6 and positive 1, so that when you multiply them, you get negative 6. When you add them, you get negative 5. So what we're saying is, in the place of negative 5x, plug in these two numbers. It's just an x, but for emphasis, I put a 1x. So negative 6x plus 1x minus 3, and then you do the factoring. So 2x is pulled out, so you get x minus 3, plus 1 is pulled out because there's nothing common there, x minus 3, but x minus 3 is common. Okay, x minus 3 times 2x plus 1. That's what I have here. So I'm just trying to give you a quick recall on that, but I will not be able to do that in every situation. So when I do algebraic simplifications, I recommend that you go back and refresh your knowledge on those concepts. All right? Okay. So we have obviously a common factor that you can cancel off. So you got that. That leads us to limit x approaches 3, x over 2x plus 1. Okay. So at this point, you see that you don't have any number that threatens us with a 0 over 0 condition. Okay. And then now you can evaluate. Evaluate, note the word value in evaluate. So when you evaluate, you're trying to find the value by substitution. So this being a rational function, limit laws allows you to plug in for x as 3. So that gives us 3 over 7. And that's what we plug in, right? Because as x approaches 3, if you were to go ahead and directly plug in for 3, because it's a rational setup, we ended up with a 0 over 0 condition. Therefore, the strategy to overcome such a situation is to factor and cancel and see if that will reduce it. And when it reduces it, then you're ready to evaluate. Then you're ready to plug in for x as 3, and that gives you a numerical answer. Okay, so what about conjugate? So all these are different algebraic techniques that we have used in the past in our algebra lessons that we're going to recall here. All right, so how do I evaluate this one? Well, we do have the root property, but that root property should have the entire function to be under the square root or under any radical. Here it's just the x plus 2 on the top that has the radical. So we have to watch carefully on how we approach this. So can we directly substitute? Well, let's try substituting. Okay, so if x is negative 1, let's plug in negative 1 plus 1. So that's square root of 1. So 1 minus 1 over negative 1 plus 1. You get a 0 over 0 condition. So this, you really cannot plug in and get the answer. So you need to get rid of the radical and see if we can apply the conjugate technique to handle this. So let's take a quick lesson on conjugate. Conjugate is an English word. It means intimate or close. So conjugate in math means that if we combined an expression with its conjugate, in other words, if you multiplied a number and its conjugate, that operation will result in eliminating the radical and producing a desirable result. So math is very close to nature. So it's like in nature, when we say conjugal love, the love between a man and a woman, when they come together, they produce what is desirable, which is the outcome is that they produce a child. So you are trying to make a connection like that in math, where if I took let's take a look at this conjugate. Let me keep it simple. Say square root of x plus 1. Its conjugate must be something that's equal and opposite, right? So the conjugate of square root of x plus 1 would be square root of x minus 1. It's equal, same terms, opposite. And then we're saying, well, we have to multiply them to get the desired outcome. So when you multiply this, what happens is square root of x times square root of x, you FOIL it, right? Will be x minus square root of x plus square root of x minus 1. Notice that this combination, equal and opposite, when they come together, then these go away. The radicals that you didn't want, they go away, leaving us with just x minus 1, a manageable expression, a desired expression, an expression without the radical. So that is the same approach we have to use here. So whenever you multiply an expression by its conjugate, you get a result that is free of the radical. Okay, so using that idea here, let's come over here. Let's say a limit. So you're taking the conjugate. The problem is coming from a radical. So you want to take the conjugate of the radical. Understand that in math, you can't just multiply anything you want. You need to balance it, right? So I take the conjugate of the numerator. So it should be equal and opposite, right? So I have the same terms, the square root of x plus 2 and the 1. The in between was a minus, so its opposite is a plus. So what I do now is this expression has to be also multiplied up and down so that you keep the balance, right? You can't just introduce it. You have to do the same thing up and down so that the effect is nullified, okay? Meaning you can't introduce a new term, but you have balanced it nicely. Now we're ready to multiply both up and down. Okay, what we understand now is that we are trying to multiply the number and its conjugate on the top, but you also have to multiply in the bottom where you won't have the desired effect, meaning you can't get rid of the radical in the bottom, but it's fine because you're trying to focus only on the numerator. So that is being taken care of. So do the simplification, please do the FOIL. So the FOIL method would be, right? And the same thing here. So it can get really cluttered. So I am going to just clean up. And give you the final expression. So I should get an x plus 2 from here, minus 1 on the top, over what I'm going to do is not distribute the denominator yet, because I'm beginning to see that if I simplify the top, I get a plus 1. So I can save this extra step of simplifying. So sometimes it pays to wait to see what happens to the top. So, you know, those two are completely gone. That's nice. So I didn't have to distribute in the bottom. It's 1 over x plus 2 plus 1. And now we're ready to apply the limit laws. So I plug in for -1 in the place of x. And there is only one place where the x occurs, and that is also nice, because then you are pretty sure that it won't lead us to a 0 over 0 condition, first of all, because the numerator is 1, and there is nothing else to plug in there. So that's going to be a 1 plus 1, so that's 2. And the answer is a half. I will move on, but if you need to take a break, you can always pause the video and continue on, right? Okay. So what about evaluating a limit by simplifying a complex fraction? What is a complex fraction? Quick lesson on that. Simply put, complex fraction is a fraction over another fraction. So you can see, you know, you have multiple numerators, denominators. Sometimes it can be, you know, a whole number over a fraction, or just a non-fractional expression over another fraction. It could be, you know, any combination of where the fraction occurs. So we come here, and the way to handle any complex fraction is obviously to eliminate the condition where you have layers of fractions, numerators and denominators, and bring it down to a single fraction, okay? A single fraction. So here you have, on the top you have a fraction, and the bottom you have a fraction. So notice that all this is to do with algebra, and the calculus part is where you apply the law, which is basically plugging in for your limit. So that is the easy part, but the algebraic portion is where you really have to do all the calculations. All right, so you look at your denominator. This denominator here, the denominator here is non-fraction, right? There's no fraction here. But here the numerator has a fraction. So your focus is obviously to get the fraction on the top simplified, and then work with the denominator to get them all into a single fraction. Yeah. So take the LCD on the top. I'm going to close this. Okay. So you have 2 minus x plus 1 divided by 2 times x plus 1. That is your numerator, all over x minus 1. I took the LCD and I combined them. Again, please take note, if you are not familiar with this, please go to your LCD lesson from algebra, refresh yourself on this, and then you can come back and continue on this. All right, so we have limit x approaches 1. That's going to be a negative x plus 1 over 2x x minus plus 1 x minus 1. Oh, you know what? I'll take it in one more step. Okay. Okay, you got that? And you have the x minus 1, right? Okay. So now we kind of simplified it in the sense that we now have a single fraction, not two fractions on the numerator itself. So we got that part done. So that is good to know. But then we still have 3 layers, right? You have 2 division bars. So you have a fraction on the top, but you don't have a fraction on the bottom. So what you do is make your bottom also appear as a fraction. And we know, again, a quick side lesson, if I had, say, 2 over 3 divided by 4 over 5, what we did was we did 2 over 3 times, we flipped the denominator, right? Became 5 over 4. Remember that? And that helped you to combine these two, and then the 2 would give you 5 over 6. Yeah? Same idea here. We are going to write this and flip the denominator. So the 1 goes on the top over x minus 1. Okay? All right. See if you can cancel anything. It doesn't look readily available to cancel, but you do see that this is x minus 1 and that this is 1 minus x, right? Minus x plus 1 is 1 minus x. So you factor out a negative 1. This is again a technique we learned in algebra. So pull out a negative. That makes, you can reverse the order of the signs. So you have x minus 1 over 2 times x plus 1 times x minus 1. And that's nice because you can now cancel them off. Just to kind of keep it contained, I'm going to continue over here. So limit x approaches 1, negative 1 over 2 times x plus 1. Okay, and then let's plug in the values. So now you're ready to evaluate. So when I say evaluate, I mean you're ready to substitute and get the value for it. 1 plus 1, negative 1 over 4 is your answer. Yeah. So this is when we use a conjugate, when we use a complex fraction to simplify the complex fraction and then apply the limit. Okay, is there a time when the limits won't apply? Maybe. So let's see. If you look at 1 over x here and 5 over x times x minus 5, we have a problem because these two functions, when you apply the limit, right? Let me show you that here. If x is 0, meaning when you evaluate, when you apply the limit, this becomes undefined. They're two separate terms, so you can kind of separate them by some law. So if I did them individually, that also becomes undefined. So these both appear undefined if we applied the sum law and plugged in x as 0. So we have to use a different strategy, just like how we had to overcome the 0 over 0 condition. Here we have the undefined condition that we have to try to see if we can overcome. So here again we use algebra. Well, one of the ways you can instantly see is to use LCD and see if you can combine them. So 1 over x plus 5 over x times x minus 5. So x times x minus 5 would be the LCD for both of them. You'll have an x minus 5 here and a plus 5 here. Okay. Again, please go back and see how the LCD is done, because we can't dwell too much time on algebra concepts here. And you've spent considerable amount of time learning these concepts previously, so it's a question of refresher. Okay, now the 5s got cancelled off, okay? And you can also see that your x's, I'm going to use a different color so when the 5s are cancelled off, you're left with an x on the top. You don't have to do it in another step. Try to get it done in the same step if you can, make sure that you're not confused. So everything's gone on the top. That means you're left with a 1 there, x minus 5. Okay. And then now it's time for you to substitute. So 1 minus 0, 1 over 0 minus 5, which is negative 1 over 5. And that is your answer.